What type of reaction do you predict for this alkyl halide here? Well, what I got is a tertiary alkyl halide with a weak nucleophile. So whatever it's going to be unimolecular. Now let's just pretend that it's going to be E1. And you say you haven't heard about E1? Well, we're now on the alkene chapter. And so one way we can form alkenes is by elimination. That's what the E stands for, elimination. Unimolecular elimination. As the leaving group leaves with its electrons, and so I'm going to have something that looks like this. And what I really want to do is, let's just call this step 1. Now here was step 2. I'm going to take some liberty. Water has unpaired electrons and can act as a base. I'm going to draw water coming over here and grabbing that proton and these electrons moving towards that atom. And that's going to give me something that looks like this, CH3 going to a... Now notice I drew these all funky. Look at this. I drew those hydrogens sticking up in the air for a reason. Let me just label this one A, and I'll label this structure A. But what if, instead, and then of course these electrons would jump down. That gives rise to a slightly different product. So there is our 2 elimination products, 2 different alkenes. And now we'll figure out why we get more of one than the other. Ready for that? Ethylene is CH2 double bonded to CH2. And all these different things can get made out of ethylene. Here's the one I'm not too excited about. So propylene, that's a common name for propane. And here would be coolant in your car. Here's rubbing alcohol. Here's your nail polish remover. This one here is the bane of society, especially here where it's windy. You like seeing plastic bags and trees. Polypropylene is what grocery sacks are made of. Get your natural grocery bags, take them to the store. So alkanes can polymerize. So here's your grocery bag. How many of you think vinyl's a cool thing and you listen to vinyl? I listened to plenty of vinyl back in the 80s and it hisses and pops. So records pressed out of this plastic. Teflon pans. Now if you're a guy, ate a lot of scrambled eggs out of a Teflon pan, certain cancer might be coming your way. Alright, forever chemicals. Alkenes can be slightly polar. This thing, because it's symmetric, isn't polar. And so we can see reflected in the boiling points. So for the most part, alkenes have physical properties very similar to alkanes. Cis alkanes have greater dipole moment than trans, so they'll be slightly polar, slightly higher boiling point. So how many of you enjoy thermochemistry? It's good stuff. And tell us, right over here, thermochemistry is going to tell us which one's more stable. And if we look at the amounts, we might tell which one's more stable. But we're going to use thermochemistry to figure that out with heats of hydrogenation. Notice these alkenes, the only difference is the double bond. And how many isomers of this could I have? It's like I could have the straight chain, I could have the double bond at the first carbon, or I could have it in the middle. If I have it in the middle, I have the cis and the trans. Then I could probably take this methyl group and move it over here and get isobutene. Anyhow, let me not digress on that. Notice once we hydrogenate this, so we have hydrogen, catalyst, and we undo the double bond and put hydrogen on it. And so the one that's more exothermic is the one that had a higher energy state. And we might say the higher energy state is less stable than the lower energy state. So this one here, we say is mono-substituted. So there's no substitution over here. We just have hydrogens. Here we have an alkene. So we call this one mono-substituted. This one here we call di-substituted because on the double bond we have an alkyl group going off that way and an alkyl group. So we say alkyl groups stabilize the alkene. And so the heat of hydrogenation here is less. So we say this one was more stable than this one up here that was less substituted. And with this energy diagram, we see that. We say this thing here is at a lower energy level than this one here. because we do the thermochemistry experiment and see that there's an energy difference. So there, the 11.3 kilojoules, presumably per mole of butene, reflects the stability between these two. So more substituted bonds are usually more stable. So here are some like heats of hydrogenation, and as we make this double bond more substituted, here's our benchmark. We haven't catalytically hydrogenated anything, but if we did, this would be about the energy difference we see. Notice the 1 butene and the 2 butene we just looked at, we have this about that much energy difference. Cycloalkanes can impart a ring strain. These bonds want to be at 109.5 degrees. They're being forced into being 90. So a ring makes major difference only if there's ring strain, either because of a small ring or because of a trans double bond. And 5-membered rings accommodate double bonds nicely, and they react much like the straight chain alkenes. Alkenes have lower boiling points with increasing mass. That's the same thing we see with alkanes. Branched alkanes have lower boiling points, less dense than water, and can be slightly polar due to this pi bond being polarizable, so instantaneous dipole interactions occur. Alkyl groups are electron donating toward the pi bond, so they may have a small dipole moment. So here we're finally to my example problem. How do we get to alkenes? What we looked at this morning we would call dehydrohalogenation. Dehydrohalogenation. So a halogen comes off and a halide comes off, and you put those together and get hydrohalogen. And we looked at an E1. We should all know what a vicinal dibromide is, as opposed to geminal. And dehydration of alcohols, in about 3 weeks you'll do this and make an alkene in lab. So let's look at a elimination reaction. This is the one I wanted to draw on the board, I think. But we have a tertiary alkyl halide, and we have a weak nucleophile. So substitution SN2, if this was hydroxide, doesn't want to occur with a tertiary alkyl. So I'm kind of jumping ahead trying to tell you all the good stuff. First thing that's going to happen is the bromine is going to be a leaving group, come off as a bromide. Here's a carbocation, and our methanol here acts as a base, pulls that hydrogen off, puts the double bond there, and now we have a protonated alcohol. Looks an awful lot like the hydronium ion to me, so the solution is kind of acidic at this point, counterbalanced by the bromide. So this is E2 reaction. This is an E1 reaction. We know it's E1 because we have a weak nucleophile, and we have weak nucleophiles, we have unimolecular stuff. So you want to memorize your weak and strong nucleophiles so you can get the unimolecular and the bimolecular predictions of what type of reaction. Okay, here we have sodium methoxide. It's the methoxide which is the plain member of this reaction. Sodium is a spectator ion. Don't put sodium anywhere on this molecule. So you might be tempted to slam this into the carbon and make a ether. But this is a tertiary alkyl halides, and tertiary alkyl halides cannot undergo SN2. So that's not going to come to play. But what can happen is this base comes around and pulls off this hydrogen. These electrons jump down here at the same time. These electrons are jumping there. All three of these things happen at once. We say that's concerted. So our energy diagram is just going to have one hump and a beginning and an end. There's no intermediate. So we're going to go back to the E1 reaction. Weak nucleophile, we say it's unimolecular, meaning one molecule is involved in the rate limiting step. Comes over here. All right, now we form the carbocation, and this thing can pull off this hydrogen. Could probably pull off a hydrogen here or a hydrogen there. Looks like if I pulled off that hydrogen, it's equivalent. We'd get the same product. Alright, the nucleophile acts as a base. The E1 and SN reactions have the same conditions. So a mixture of products will be obtained, which means this thing could slam in there and form the ether. So what are the main points of the E1 mechanism? Ionization to form a carbocation. Halide leaves, form a carbocation. Solvent extracts a proton from to form an alkene. Grabs that proton, those double bonds. So the rate limiting step is the halide deciding to leave. Valley is the intermediate, the carbocation, and then base comes along, pulls it off. That occurs at the second transition state, and you get your alkene. E1 and SN1 have the same first step, formation of the carbocation. That's the rate limiting step. Zaitsev's rule says if more than one elimination product is possible, the most stable alkene is the major product. So notice here are two different hydrogens. So here's where I learned to draw it that way. And so this product, we say it's maybe tri-substituted. This one here, we say it's di-substituted. And we get more of this one. So that's what nature wants and enjoys. So now over here, which one's going to be the major product? Yeah. So on a quiz, if it said circle the major product, it's more highly substituted than the other one. You could either pull off one of these hydrogens or this hydrogen, pull off one of these hydrogens, we get this alkene, pull off this one, we get this one, and this would be the major product. What's the 2 stand for? It says require a strong base, which is typically also a strong nucleophile, so it's bimolecular. So here is a tertiary alkyl halide. And so it might be tempting to say, oh, alkyl halide, nucleophile, slam that into this carbon that leaves, and we form an ether. But you want to remember that tertiary alkyl halides cannot undergo SN2 mechanism. So that's why they crossed out these arrows. Now what can happen is base comes around, sees this proton and says, I can pull this off. Those electrons jump there, and the leaving group leaves, and we form this alkene. How do chemists know this is a bimolecular event? Because of this rate law. We double the concentration of methoxide, we double the rate. We double the concentration of T-butyl bromide, we double the rate. So here the E2 mechanism prefers tertiary alkyl halide, followed by secondary, and then a primary. A mixture may form, but the Zaitsev's product predominates. What that means? What does that mean? Zaitsev's rule says we form the more highly substituted alkyl halide. Any questions about this? So this is Zaitsev's product. It's more highly substituted. So tomorrow we'll learn about the Hoffman product when we violate Zaitsev's rule. You won't want to miss that.